The problem I chose for this problem of the week is number 35. So for this first step, we're going to find our critical points. So for us to do that, we have to find the derivative of this function right here. So remember, the inverse of tan is 1 over 1 plus x squared. It's basically the same thing as 3.10. We're just using the inverse of tan. So you're going to take the inverse of the top right here, and you're going to multiply it to this fraction right here, and then you're going to combine them into this, and then you're going to combine it further into this, and then you're going to equal it to 0. So then you get here, and then your critical point is x equals 0, and we get no critical points for this one because, as you know, this is a -3, so any number we get is just going to be an imaginary number, and we don't want an imaginary number. Next step, same exact thing, but we're going to find the second derivative. For this one, because it's a fraction, there's multiple different terms, I did f equals 6x, the prime of f is 6, same thing for g, and then I did the quotient rule, and then I combined through multiplication for here, and we got to here, and then I added these two terms right here to get this, and then I kept combining, and then because these basically are two different terms, they both have squared on them, we just simplify it. So I took the root off of the square, so then I have this 3 and then this 18, and I cross them out, so we get a 1 and then a 6, and then we simplify our answer to this quotient right here. And then our next step is to find the inflection points. Same thing with critical points, we're going to equal it to 0, and once we get all that, we get x equals plus or minus 1, because those are our possible inflection points. The same thing, the same issue we had over here, we're just going to get a negative number for the to be squared, and as we know, it's just going to be infinity. Step 3, we're going to check our slope changes, verify our inflection points, and find our concavity. So for f prime, as we know, our critical point is x equals 0, so we're going to find a number that is less than and greater than 0, and then we're going to test it into the first derivative. And when I tested it, I got negative or negative slope for -1 right here, and then the same for this one, but I just got positive. Then we're going to move to this one, exact same thing with the numbers and the testing. I got concave down, concave up, and then concave down. So now we know that our inflection points are x equals 1 and x equals -1. And then also for this one, we know that x equals 0 is a local minimum because we start with negative and then we go to a positive slope. Next, we're going to find possible asymptotes and domain. The domain for this function right here is defined for all real numbers, so we just have negative infinity to positive infinity. And for our asymptotes, we have the fraction going to x to infinity, and we just plug in the infinity, and then we just get an infinite number, and that goes to pi over 2. The same thing for the negative one, because this is negative and this is a square, we know that we're going to get a positive, so that's going to go to pi over 2. It's basically just the asymptotes for the inverse of tan graph. And then we have no vertical asymptotes because our function is defined for all real numbers as our domain is not restricted. And finally, we're going to put that all together and we're going to graph our function. So I just have a little key over here just to help us remind us what exactly our graph is going to look like. So for asymptotes, we have none for vertical asymptotes, and then we have pi over 2 for horizontal. For central points, or critical points, sorry, we have x equals 0, and we know that this x equals 0 is a local minimum. And then for inflection points, we know that we have x equals 1. I forgot to put x, it's also x equals -1. I just forgot to put it down. And then for our slopes, we have a negative slope and then a positive slope from 0 to negative infinity, and then from 0 to positive infinity. That's what that means. And then we have our concavity right here. So this is going to be a concave down, concave up, concave down. So let's check. So we have a horizontal asymptote, okay? We have our inflection points at -1 and 1. So here we're concave down, and then we're switching at this point to concave up, concave up, concave up, and then we go to this point, and then here it is concave down. And we know this is concave down because it's like an umbrella. If rain were to fall, it would fall off. This is concave up because if rain were to fall down, it would collect over here. And then for our critical point, this is 0 right here, and that is the local minimum for this area right here. So after looking at it, we can confidently say that our graph is graphed correctly.